Should be yeah, I don't know solutions. No.
Hello, good morning. We had a homework due today, and the new homework will be due on Wednesday. Earlier, I had said it was Friday. Homework 3. Since I earlier said it was Friday, I will keep it optional. Try to do it by Wednesday. It's possible to do it. I'll be finishing the necessary concepts on Monday. But since I had earlier mentioned that it would be Friday, it would be available for you until Friday. But for your benefit, I would say go ahead and aim for Wednesday if it is possible. Midterm 1 is on Friday, 1 week. Today, I'll be posting old exams. I'll be posting all the exams I have available. Like I've taught this about anywhere between 3 to 6. I never counted it. So I'll post all the exams. It will be available on the course web page. Probably today will be posted. Page on course. And about the midterm itself, how you want to prepare lecture examples. I said this before. Lecture examples. Homework examples. And our textbook, worked out exam. Textbook. If you think this is too limited set of examples, there is a good chance that you're not exploring the particular example in detail. You're only superficially looking at it, only the mathematical steps. That's one way of I don't want to blame anyone that that's not the right way to study, but that's probably one thing you could question if it is too. If you think that, oh, everything is easy, then probably you're not exploring the fine features in each problem. That's just a small, tiny advice. Don't take it too seriously, but that's my recommendation. And what else? Yeah, there will be, I think, so this is a 50-minute exam. So this will be on Friday during the class hours. Expect about 8 to 10 questions. 8 to 10 questions. Out of that, breakup might be, let's say 3 plus 5 or 4 plus 6, right? Or 4 plus 6. That means here this 4 will be conceptual, and this will be problem based. That means to say that the 6 questions will be exactly like the homework problems that you have seen. The conceptual questions will be much simpler, but it will come somewhere you have used it in solving the problem. For example, what is the electric field inside a conductor, right? That could be an example. And the answer is simple, it's 0. If you know it, you know it. If you don't know it, probably you might be completely lost. Something reasonably straightforward, doesn't need too much work as far as mathematics goes. Is that clear? Did I describe that more? Any more description? Okay, good. Okay. And feel free to ask me anything you would like to know more on. Okay. We are losing students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 12. That's only half the class. We are supposed to be 26. So I guess, yes, I cannot do much. Okay. So, okay. And if possible, remind me to move the cameras. That should be. I think last video I checked and it is pretty much useless if you're wanting to gain anything out of it. But anyway, my apologies on that. Okay. We did spend a good amount of time on the first chapter of the book, and I should, yeah, that's also useful. This is chapter 18, complete chapter 18. There's only one chapter. The full chapter 18 is what we'll do, and the next week or so we will do chapter 19 and so on. Like we'll follow the book pretty much in order. Okay. We introduced the idea of electric field, first the idea of electric charge, then the electric force and the electric field. Those are the three concepts we have introduced. Let me write that down. So electric charge, it's letter Q we have been using, but it's not necessary that you stick to that letter Q. So there is electric force, which is information about Coulomb's law. Electric force, and I prefer to call it the force in the sense that then it connects with whatever you've done in the earlier semester. You described a system using forces, and now you can describe a system using this particular force. You can do the kinematics of that. And we introduced the idea of electric field, which was related to the force. So it is force per unit charge was the electric field. It doesn't have to be a point charge system. We also stressed that there are two configurations we talked about. Like in general, you can have a lot of configurations of this charge. How you place these charges matter. And the first case we did were point charges. Or something, point means it's a sphere of 0 radius. So any spherical charge distribution also is a representation of a point charge. And the second thing is parallel, or it doesn't have to be parallel, planar charge. It is planar charge. So that means you have a plate and there is a charge you uniformly distribute on that plate. And we showed, or we suggested that, or we qualitatively argued that the electric field associated with that will be a constant everywhere, whether you are close to it or far to it. Very similar to the idea of gravitational field being constant on the surface of Earth. We will be able to show this more logically, let's say, derive this, that in fact electric field is constant using the idea of Gauss's law that we want to do today. So let's talk about electric flux. It's a concept related to electric field. So let's have the, let's remember electric field due to two point charges. One is positive and the other is negative. If you have these 2 point charges, since one is positive, we pointed out that the electric field originates from a positive charge, or it has to originate from infinity. That's only 2 possibilities. Here we have a positive charge, it originates from there, and then it ends in a negative charge. That's necessary. It cannot just magically emerge from a spatial point. So this is a source of an electric field. This is a sink for an electric field. Completing the diagram, it looks like this. It's pretty much, if you're seeing the magnetic field configuration of a bar magnet, if you think of this as a magnet, that's very similar, like Earth's magnetic field looks like this. So that's your electric field. Again, notice that a positive charge, so source of electric field is positive charge, right? So positive charge. And sink of electric field is a negative charge. So that's a clear point we have made. Then that would mean that if I get closer and closer to this positive charge, what is the connection between the electric field and the source? Is there a complete rigorous definition or a connection between how many electric field lines come out of this positive charge and how many go into this? For example, it is clear that if there are 10 lines we draw out of this, 10 lines have to go into this, at least this point negative charge. If there are more, if there are 10 positive charges and 3 negative charges, still the number of lines that originate from here has to go into any one of those charges. So it seems like there is a connection we can draw there, and that's the idea of electric flux. This will be a measure of how many electric field lines come out of a positive charge. For that matter, we will talk about any area. So we can talk about any surface here, and that should be the same. It doesn't matter whether the surface is very close to a positive charge or very far from a positive charge. So let's define this better. So the electric flux, again, in a rigorous manner. Instead of having that description of electric field which is curved, so let's have a parallel set of electric field lines just for simplicity. So that's your electric field lines. It is filling this whole space. It can be coming out of the board. It is not confined to the plane of the board alone. And let's have a surface. Let's say this is a surface. It is again coming out of the board. So this is a surface, not really a line. So this is a surface of area, let's say A. And these 3 lines I have shown are electric field lines. Okay. Let's have the electric field line described by a uniform set of lines that will be a constant E. Some electric field, for example, 1000 Newton per Coulomb, some number times the direction, that's a vector, so magnitude and a direction. Let's say this is Z direction. So this is Z direction. So electric field, there is a strength of so much and it is flowing in the direction of Z. That's electric field line. Now we have an area like this. So area now, And the first thing we should ask ourselves is area a scalar or a vector? Is area scalar? Suppose I pose it as a question. Any comments on that? Scalar. Anything else? Any other comment you want to make? Actually, that's okay. The way we usually look at area, we always associate a number with it, right? What is the area of a sphere? We say 4 pi r square. We never say what's the direction of the area. But more accurately, area actually is a vector. Okay, sorry about that. The area is a vector. So then the question comes, what is the direction of it? Okay, especially for the surface area of a sphere. What do you mean by like it is pointing in all directions? So what's the area of a sphere? But we are talking about a plane here, right? So area is, the magnitude is of course the usual area we talk about, but it has a direction. And think of my palm. My palm has an area. Its direction is perpendicular to that. Right? That's a unique direction you can associate as far as it is flat. And if it is not flat, then there is a problem. We will come to that. So in this case, this is the direction z hat. Is that unique? I just said it is unique. So if I say my hand here perfectly flat, let us say, if you imagine this to be a flat surface, and I say perpendicular to my hand, is that a unique direction? Notice that this is perpendicular, but that's also perpendicular. Right, this and that. So there are two directions apparently. I can do this in here. And always you have to, we will always have a surface which encloses something, and the direction will be coming out of the closed surface. In this case, it is not clear whether it is this way or that way. Then you can choose whichever you want. It doesn't matter. But always the one that is pointing outward, if there is a closed surface, is what will represent. So in this case, we'll choose this to be A times C hat. What about the area of a sphere? Since I mentioned it earlier, let me point out. So this is a sphere. Now I had to break this into tiny, small surfaces. It has to be really tiny because otherwise there will always be a curvature to that. So you have to really take the limit that these are tiny, tiny surfaces. And then you have to add all this area. Each of this has an area associated with it. And if you vectorially add them, then the area of a sphere is actually 0 because they will all cancel out, right? There will be an area down here, so they will always cancel out. So if you vectorially add the area of a sphere, that comes out to be 0. But typically, what we do is we're talking about the magnitude, that is the surface area of a sphere, is when you take the dot product of this with z hat, and that's how we are at it. But that's, having said that, we want to have the vector interpretation of an area, and now we have an electric field and an area vector, and we would like to know how much of this electric field is going through this area. Remember, this area I can move, right? Think of a bucket of water. So this could, imagine this to be a bucket of water, and this is the face of the bucket. Would you say face or the opening of the bucket, right? That's what it is. And this is a flow of a quantity. This is a flow of water. And if you want to collect the water in the bucket, you will always have the face perpendicular to the water. That's just, we just know that that's a skill we develop from the evolution. But now, if you will never put it like this, right? That will be really not appropriate if you want, if water is flowing here and you have a bucket which is you're immersing it in this direction, there's a good chance that if everything was moving perfectly flat, no water will get into the bucket. So we want it in this direction. So we want to measure the flux. So flux of water in this case, or flux of the electric field, will be defined as, so this is flux of electric field. How much of the electric field is going into the surface, like how much you can collect it in, that will be represented by the letter phi, that's a Greek letter. So, and you put in a subscript E underneath because later on we will talk about magnetic flux also. So being prepared with that, we will call this with a subscript E. That will be equal to the dot product, scalar product, the vector dot product of electric field dotted with the area. That's it. And what is the dot product mean? You must have used this in your first semester when you did the work done by efforts. This is the same dot product that came up. But if you're not familiar about it, it is basically the magnitude of the electric field times the magnitude of the area electric field, and the cosine of the angle between them. Okay. Between the two directions. Notice it is very tempting to think that area has a direction in this manner. No. Area's direction is not in the plane, it is perpendicular to the plane. So the angle between the magnetic field and the z direction is in this case 0. So there is another possibility that you could have this area in this band. Right? That's the same area here, but this time area vector is in a different direction. Let's call it n hat. And now it makes an angle. That makes an angle now. That's the angle we are talking about. If you rotate this surface, this area vector makes an angle 30 degrees or 60 degrees with respect to the electric field. And that's what we are interested in. So let's do a simple exercise. Just to describe how this is calculated. So let's do some illustrative examples, let's say. Come on. Okay. Example. Let's say same situation here. We have a perpendicular to that. And let's say the electric field is equal to E times Z hat, where E is equal to 450 newtons per coulomb. You can also say electric field is 450 newtons per coulomb Z hat in a single line. The area A is equal to, let's say, 10 centimeters square, like if you have a bucket or something. So typically that's about 10 centimeters square. So that's 10 centimeters square. And its direction now, in this case, notice it is again in the same direction as Z. So that's Z hat. And convert the units. 1 centimeter is 100 meters, but there are 2 centimeters in here, right? There's a centimeter square, so centimeter and a centimeter. So you need to convert that 2 times, so that's 10 raised to minus 4. So that's 10, let's say. That's 10 times 10 raised to minus 4. Minus 2 is what you get for a meter, so that's 10 raised to minus 4 times meter square times the hat. Unit is meter square. So what is the flux is equal to electric field dotted with area. I want to do this slightly differently. I'll write this as E and then Z hat. And area vector has a direction Z hat also. So that's Z hat here. I write the direction of the area vector first. And then there is an A. That's basically the angle between the 2 vectors, right? 2 unit vectors, dot product is basically the angle between them, but this angle is 0. This is 0 degrees here. So that's cosine of 0. which is equal to 1, which makes it electric field times the area. So that's the maximum value you can get out of that. And you have 450 times 10 raised to minus 3. If this is 10 into 10 raised to minus 4, it's 10 raised to minus 3. And this electric field is Newton per Coulomb times meter squared. There is no special units for the flux. That's 0.450. That's Newton meter squared. Let's do the same exercise again with when it is making an angle. In an example, so you say same set of lines, electric field lines, same electric field here, same area also, but now let's say it makes an angle. Let's say this is making an angle. Now I should be careful about what is the angle it is making. Often you say that this area itself is making an angle. It depends on the diagram that I give you. So if I were to tell you that this angle is given, that is what we are interested in, but sometimes you are given this angle. So that's, let's say, 30 degrees. If I tell you that's 30 degrees, but that's not what we are supposed to use. We need to use the angle between the electric field, that's z hat, and the area vector. So this is the direction of area. If this is 30 degrees, that's 60 degrees, and right, so this is going to be the same again. So you would have thought that, oh, this will be slightly different, but that's again 30 degrees itself. So it is exactly that same angle. And what you learn is that z dotted with n, in this case, is cosine of 30 degrees, which is 0.87. If you use your calculator, that's what you get. So the flux is equal to, again, E times Z dotted with N this time, times the area A. Again, put in the numbers, so that's 450. So let me get some space there. So this is 0.450. And then I can erase this. And here we have 450, 0.87, and area was 10 raised to minus 3 in SI units, right? Everything in Newton per Coulomb and meter square. So that's same as 0.450 into 0.87. So it will be slightly less than the earlier one. And that's 0.39 to Newton meter square over Coulomb. Clearly, it is less. You can actually go to the extreme scenario now. Like, let's say a third example. And let's say you have the same set of lines. And this time you really keep the area in the same, at least if you think of a plane as a direction, then it is in the plane, electric field parallel to the plane. And the vector n is in this case here, which means that this is 90 degrees. what will be the flux for the scenario? Yes. It will be 0 exactly, because cosine of 90 comes in. Z dotted with n here is cosine of 90, that's immediately 0. That means no electric field is crossing this plate. The electric flux is a measure of how many lines are crossing the plate, and flux is immediately 0. You don't even have to do the calculation. You know that cosine 90 comes in, that's 0. Intuitively, because there are no lines crossing this plate, mathematically, because it is two vectors, area and electric field, is perpendicular to each other, so they're not crossing. They're not crossing each other or crossing the area of the plate. So that's the idea of electric flux. And what we want to do now is go back here, a positive charge, and ask how much flux is coming out of this positive charge. Right? If this was a flow of water, how much water is coming? If you were to collect all the electric field that is coming out in a closed sphere around it, on a closed surface area around it, how much of electric field is coming out? And that's a nice little concept, and we will see that it is universal. It will become a theorem, and that will help us derive new things related to electric field. So let's go back and try to calculate it for a sphere. Let me move this before I forget. So here, let's say this is electric flux. Coming out of a point charge due to a point charge. Again, electric flux means how much of electric field is coming out, what kind of source it is. If you had what is the source of water? It is your sink pipe, right? So how much of water is coming out of it, and how much is going in, if you want, if it's a negative charge. So that's what we are talking about. So we have a positive charge. Let's see a positive charge. And its electric field lines this time is coming out of this positive charge. They go like this, radially outward, making it uniform lines. So that's your electric field coming out of this positive charge. I want to calculate the flux. So obviously, if I want the total flux coming out of this positive charge, I want to enclose this whole positive charge somehow and use a sphere just for ease of calculation. I will make it a sphere. So my area, so electric field is clearly, this is the electric field due to a point charge. I know what the electric field due to a point charge is. That is r hat, its direction, or let me say first 4 pi epsilon naught. And then there is charge Q. So clarify that that is a charge Q. So let's use capital Q. Capital Q over r square. I'm keeping this positive charge at the center, that means at the origin. And how far I am from the charge is the distance r. By how far means the observation point is a distance r from it. So anywhere here will be r. I want to use, and that is the direction r hat. In this case, it will be radially outward, right? Or they're all radial directions. That's your electric field, which we know for a point charge. Now I want an area. So area, I have to decide on what's going to be my surface area. I want to enclose it. I close the whole positive charge. So I pick a sphere. So let me pick the area to be a sphere. It is not a physical area in the sense you don't really use a blanket or something. So it's an abstract area. We are imagining that that is an enclosed surface and we want to calculate the electric field going through that surface. How much of electric field is going across that surface? If it's a sphere, I want to add up all these tiny elements here, and all of them is r hat, right? Its direction is r hat, all these tiny elements. So I want to think of it, maybe right way to say this is that this is the sum. So read this letter as sum. Sum of small areas, each of that has r hat times a tiny area element. So this, let's say this is A. So small areas, like infinitely small areas. That's just the idea that I'm breaking this into small areas that I talked about, because I want to think of it as a vector. If I think of the whole area as a vector, then it will be 0. So I don't want to do that. So I want to first take small tiny area, calculate how much electric field is going, then do it here, how much is going in this direction, and then add up all those quantities. Notice that the flux would be clearly just multiply these two quantities, and you notice that this will be equal to sum of all the quantities. We have first the electric field. So this is 1 over 4 pi epsilon naught Q over r square r hat, and then multiply it with the area. And this is our area element if you want. So that's again r hat times A. So this is the tiny element of area. That's the electric field going through that tiny element of area. If you want, that's the tiny element we are talking about. And we want to add up all those. So first calculate this and then do the whole sum. But before we do the sum, we realize that there is a dot product that is coming in, and both are in the same direction. Electric field was radially outward. Each of this area element is perpendicular to the radial direction. So the direction of this area is always radial, and that's cosine of 0, which is 1. So that takes care of the directional nature of it. It was crucial because remember, if it was perpendicular, it is 0. So it was a choice we made that it is spherical, but it will turn out that it is independent of that choice. That's the remarkable part of it. And we need to multiply. So if this is gone, then we just take this a tiny element times this electric field. This is a sum. I'm adding all these quantities. When you notice, this is the same at every point as far as the magnitude goes. Now that the direction is gone, the magnitude of the electric field at this point is exactly the same as the magnitude of the electric field at this point. Its direction is different, but its magnitude is the same because 1 over r squared, the radius is exactly the same. So that comes out of the sum. So I can do this as, so conceptually this was a big leap, that I'm saying this comes out of each of this sum, and I can take the sum inside and say this is A. Add up all the tiny sums. And why is that? Because this is a constant in the sense for every tiny element, it's the same electric field you multiply because you're staying the same distance away from it. Its direction is different, but direction went away in taking the dot product, and the magnitude is exactly the same. So due to that reason, the sum goes into the, or this can come out of the sum, and then it is easy to do this summation of the area. What is the sum of all the tiny areas that I add up for a sphere, and this is the magnitude of the area I'm doing So this is the surface area of a sphere. So this is 4 pi r square. That's the surface area of a sphere. So let me write that down here. So flux, that is the total flux that is coming out of a point charge, is equal to 1 over 4 pi epsilon naught times q over epsilon naught times the surface area of a sphere, which we know is 4 pi. Oh, what did I do this? That's q over r square. Sorry. Q over r square, and surface area of a sphere, that's 4 pi r square. There's a lot of cancellations there. 4 pi goes away, r square goes away, and what is remaining is just the charge q and an epsilon naught. So we went on to ask how much electric field is coming out of this point charge, and it is just the charge itself up to a scale. This is a constant divided by epsilon naught. That's your amount of electric field that is coming out of it. This is, even though we did this for a point charge, this can be generalized easily, and this is what Gauss's law is. So let me quickly state Gauss's law, and we will use it next time. I think it is okay to, when there are two S's, I think you write the S afterwards, I suppose. Check on it. I think you put the S there. Okay, what does Gauss's law say? If you have an electric field lines due to any configuration, so pick your favorite configuration, and the flux that's coming out of a closed surface will always be equal to the enclosed charge enclosed. Maybe I should write Q enclosed over epsilon naught, where this here means charge is enclosed. Maybe this is not showing up. Charge is enclosed inside the area. So let's do a simple example, and in the last 5 minutes, and we'll come back and use Gauss's law for other purposes next time. So let's have a configuration. So example. So let's have, so this is your origin. It's just a reference line. Notice that this is 0, 0. Let me, yeah, so this is 0, that's 1, that's 2, let's stick to 2. And this is -1, that's -2, right? That's just a reference. So this will be 0, 0. A point here, if this was 1, this is 1, 1. Let's make a simpler problem. Sorry. I'm making it too complicated. Let's just have a lattice of charges. This is positive charge, that's negative charge, positive charge. This is positive charge, that's negative, negative, positive. I think the pattern is clear. Positive, negative. Oh, did I mess up? Minus, okay. And it keeps going. Positive, negative. Let's do one more. Okay, so and it keeps going. Let's say the pattern is clear, and each one of this is plus or minus q. Each of these charges is either plus q or minus q. Let's say this distance is a. Like this, each of this distance is a. The lattice are made up of equal distances. The idea is that I put in a sphere now, or this is a flat sheet. So let's say this is a cylinder. And let us say this is 2 times A. So that it doesn't capture these charges, but it captures 4 of them. And it is clear now, if you were to draw the electric field lines due to this, this is really complicated because there are field lines coming out of this, then they go into that, they can actually go in here, but they have to avoid this positive charge, they will go here. So there's a lot of field lines you have to take care of, and that's not easy to draw. But without drawing the actual detailed electric field lines, we can ask what is the total flux of electric field that is coming out of this cylinder? What's the total flux of this? That's a question one can ask. Is the electric field as a whole coming out of the sphere, or is it going in? Right, that's a simple question one can ask, that how much total energy, for example, is coming out of the sphere or going in, or in this room, how many people are going out and how many are coming in. But we don't have to worry about the total electric field lines for that. According to Gauss's law, we just count the total number of charges inside. That's all we need to do. And we said each of this is positive charge. So we will do, there is an epsilon naught in the denominator. Just add, right? There is 4 of them. This is negative q plus q, negative q plus q, and 0. So total electric field lines is coming out of this, right? But that doesn't mean that there are no electric field lines here. It just means that some of the electric field lines are going out, some of them are coming in. The total of this plus and minus is coming out to be 0, and we will use more features of this next time. I'll stop here. Thank you.